Welcome to Seismic Shock Response Spectra, Complex Oscillating Shock Pulses, and I'm Tom Irvine. Hope you enjoy this unit today. So here are some civil engineering structures. And we'll start at the top left. There's a water tower, and then going clockwise, then the Transamerica building in San Francisco, then a smokestack, and then a launch vehicle on a stool at Vandenberg, California. More about that one later on. We've got a bridge at the bottom, and then we've got a cell phone tower or telecommunication tower of some sort. And what we'd like to do as a first approximation is model each of these large structures as a single degree of freedom spring mass system and then subject it to a base excitation. And we're going to go through some sample calculations for that today using the Centro earthquake acceleration plane history. Now these are large structures, but we can have smaller equipment, like maybe a heating, ventilation, and air conditioning unit that we would also apply this same type of model to as well. So our earthquake today is going to be the El Centro Imperial Valley earthquake, and this was in. And sad to report that 9 people were killed by this earthquake. At Imperial, 80% of the buildings were damaged to some degree. In the business district of Brawley, all structures were damaged, and about 50% had to be condemned. The shock caused 40 miles of surface faulting on the Imperial Fault, part of the San Andreas system in Southern California. And the total damage has been estimated about $6 million. And I assume that was in 1940 dollars, so in today's dollars, it would be some scale factor much higher than that number. And the magnitude was 7.1. Now, this is an important earthquake because it was the first earthquake for which good, strong motion accelerometer data was measured that could then be used for engineering purposes. And strong motion means that the accelerometers were fairly close to the epicenter of the fault itself. There's actually a triaxial accelerometer. We'll get to that shortly. But we're still using the El Centro time history and its shock response spectrum even today in engineering. So let's go to our main GUI package, and we'll go to import data, or to library, then seismic, and then time history. And let's do NS. Now that's north-south. So horizontal to the ground in the north-south compass direction. There's also an east-west component, and up is vertical. And of those 3 components, north-south is the most dramatic, and that's the one we're going to take a look at. Here it is in the time domain, acceleration g versus time in seconds, El Centro north-south component. And it's really interesting, if you take a look at this pulse, if you were to take away the numbers from the x and y axes, that looks like a pyrotechnic midfield shock. So it's really interesting. I come from a world mostly from aerospace, and that does look like an aerospace pyrotechnic shock is measured in the midfield. But it's different in the sense that in earthquakes, the energy is down at much low frequencies, mostly below 10 hertz, and pyrotechnic shock, most of the energy may be well above 1,000 hertz. But we do have numbers. In fact, the peak acceleration is 0.35 Gs. Now, 0.35 Gs might not seem that it has much damage potential, but there's definitely more to that story because we need to account for the duration as well as that frequency content goes along with it. So let's take a look at a spring mass model, single degree of freedom. We have mass m, Hooke's law gives us the stiffness k. We have a dash spot with viscous damping coefficient c. We've got y double dot for the base acceleration and x double dot for the absolute acceleration of the mass. And to derive a governing equation of motion for the system and then solve it. So on this slide, we have that same spring mass system that is subjected to a base acceleration. To its right is the free body diagram. Now there's no direct external applied force acting upon the mass, but there are two transmitting forces, one arising through the spring and the other arising through the dashpot. And here we have K for stiffness, and then in parentheses y minus x. Y is the base displacement, x is the absolute displacement of the mass. And then y dot is the base velocity, and x dot is the absolute velocity of the mass for its response. Newton's law, sum the forces in the vertical direction, and we come up with this intermediate equation of motion, which, by the way, we usually cannot solve because a base acceleration, or input is base acceleration y double dot. And on the right-hand side, we've got y dot for base velocity and y for base displacement. Now, what you might think is we could just take that base acceleration and we could integrate that to get base velocity, and once more get base displacement. Now, wouldn't that be nice? Yes, it would, but to carry that out, we need to know what's the initial base velocity and the initial base displacement. Seldom are we going to know those. Well, we got a very creative and useful workaround. We're going to take the relative displacement z equal to x minus y, so that's the absolute displacement of the mass minus the displacement of the base. We'll do a substitution, as shown, and then we come up with a second order ordinary linear differential equation. It's got constant coefficients, and it is non-homogeneous because of the term on the right-hand side. The term on the right-hand side is what's called an inertial force. It's not a true external applied force, but as far as solving this equation, that's just a very minor point. So let's go through and divide through by mass for simplicity. Make it a little more neat and tidy. And then by convention, we're going to take the viscous damping coefficient C divided by the mass M. And that will be equal to 2 times the viscous damping ratio times angular natural frequency. Stiffness K over mass M is equal to the angular natural frequency squared. Damping ratio. So by substitution, we come up with this final form equation. Now, this equation is pretty interesting because we don't see explicitly mass, neither do we see stiffness. We could say implicitly mass and stiffness are contained in that natural frequency term as well as this term that was substituted for the C over M. So mass and stiffness are making their presence known, but as long as we've measured the natural frequency and measured the damping, we're good to go without accounting for mass and stiffness. Now we can also do an analytical prediction of angular natural frequency, but there's no analytical prediction for damping. That's got to be measured. So natural frequency measured or analyzed by a model, maybe finite element model or spring mass model or some sort of model. And then damping, you're on your own to measure that, although there are statistical databases to draw from. Now we got to figure out next how to solve that Darwin equation of motion. And here it's copied and pasted onto this slide. Now y double dot could be a sine-based input in another context. And if that were the case, we could use Laplace transforms to solve this. And if you can use a Laplace transform, you should. But that's not going to work for us today because y double dot is going to be a complex oscillating shock pulse or earthquake pulse waveform, transient waveform, which we call an arbitrary function. So we've got a method to deal with that on the next slide. And then we're going to go through and solve for relative displacement c. Then we can take the time derivative to get the relative velocity and take the time derivative yet again to get the relative acceleration. Now, once we get the relative acceleration response, we can add that to the base acceleration response to get the absolute acceleration response of the mass. So primarily what we're looking for is the relative displacement z and the absolute acceleration of the mass, x double dot. We're also going to be talking about pseudo-velocity, but that'll be in a couple slides from now. Now on the left is just kind of whimsical, but my wife and I have had the chance to go to Europe a couple of times. And I noticed over in Europe, there's kind of this deli that sells healthy foods, and it's called Laplace. And in Geneva, Switzerland, there's an FFT. Well, that stands for fruit for thought, but in my world, FFT is a fast Fourier transform. So kind of thought it was funny to see these kind of bakeries or delis that have names that come to us from signal processing and solution methods in vibration analysis. A little bit of humor. Okay, so what about these functions that vary arbitrarily with time, like complex oscillating shock pulse, including pyrotechnic, including earthquake? Well, the textbooks would have us go off and do something called a convolution integral. We can have a convolution series as well. Those are a bit inefficient to solve for our purposes, so we prefer to use a numerical method, and our method is going to be the Smallwood ramp invariant digital recursive filtering relationship. It's very efficient and it's very stable. Being a numerical method, it will not give the exact answer, but it will give the nearly exact answer. And I've got a link there that you can go to look up the Smallwood's, several of his paper, including his original one on the ramp invariant digital. And I'll put that link directly into the description on the YouTube video, make it easier for you to. Well, here is the Smallwood algorithm, and x double dot sub I. So the absolute acceleration response at step I is equal to this coefficient. Okay, now you're going to see this coefficient one more time today. But here it is in the response absolute acceleration, and the response acceleration at step I depends in part on the previous response acceleration, x double dot sub I minus 1, minus this coefficient, which you'll also see again, times the absolute acceleration response at x double dot sub I minus 2. Now these first two terms form a feedback loop, or that's the recursive part. And if you're designing a control system or an electrical filter or some type of algorithm, it's always a good idea to have recursive or a feedback loop, because that will greatly improve the chances that you'll have a stable algorithm or a stable control system. The feedback loop does not guarantee a stable control or stable numerical results. If done right, it will give a stable result. In fact, that's why we do our shaker table test in the lab for vibration-based input test. We have the feedback control accelerometer for that very reason. And then the absolute acceleration response, x double dot at step I, depends also on the current-based input, and then this long set of coefficients times the base acceleration 1 times delta del, plus this long coefficient times the base acceleration at step I minus 2. Now omega sub d is the damped angular natural frequency. Omega sub n is the undamped angular natural frequency. Have square root underneath 1 minus the viscous damping ratio squared. And delta t is the time step, and it's the inverse of the sample loop. Now the reason this is filtering is that spring mass system is a mechanical filter. We'll go back a few slides and take a look at that. So that system, again, it's a mechanical filter, and we can make an analogy to an electrical circuit that has a resistor, an inductor, and a capacitor. And there are certain properties of that system, such as its natural frequency and damping. And then depending on those properties, as well as the nature of y double dot and its characteristic, then the spring mass system, it may have dynamic amplification, like resonant amplification, where x double dot peak is greater than y double dot peak. It may have attenuation in other cases where x double dot peak is less than y double dot. And under certain circumstances, x double dot peak may equal y double dot peak as well. So this system can either amplify or have unity gain or attenuate base input energy, and that's why we call it a filter. And that filtering action then is reflected in the Smallwood algorithm on this very slide. So next up is going to be a companion. It's going to be the relative displacement, z. And there's those two coefficients, like I told you, would be present yet again for the recursive or feedback loop. Only now we've got relative displacement instead of the absolute acceleration response. And then the remainder is just a pretty simple term here where we have the y double dot base acceleration at step I minus 1. Okay, back to the MATLAB GUI package, and let's just go to this, got this oval here around this button called SDOF response to base input and applied force. Let's click on that. It's a shortcut. So we come to this script, which calculates the response of a single degree of freedom system to an applied force or base input time history. And we have then El Centro north-south, which we called in earlier. And we have 1.8 hertz natural frequency for our example today. So imagine we're applying the El Centro north-south then as a base input to a structure. And pick out whatever structure you want. It could be a cell phone tower, a water tower, a bridge. It could be a launch vehicle on a stool, a launch pad. It could be a building. Just take your pick. And we've got a Q value of 10. Now that's equivalent to 5% damping. Go to base acceleration to calculate, and there's a note here that the numerical engine is the Smallwood ramp invariant digital recursive filtering relationship. Calculate, you will get a couple of plots, and then what you'll also see then is the peak acceleration response will be 0.92 Gs if we round off. And then we've got a peak relative displacement if we round off of 2.8 inches that is. So what we like to do is just take the peak absolute value. So we'll just say the peak absolute relative displacement is about 2.8 inches. We also have pseudo velocity coming in at the peak absolute of 31.3 inches per second. More about pseudo velocity in a few slides. So here is the base input acceleration on top, acceleration in G's versus time in seconds, and that's the El Centro north-south that we called in earlier. And then on the bottom is the response for the oscillator, so the model of our building or bridge or tower, which is 1.8 hertz and Q is equal to 10. Now the y-axis scales are different, just note that. And of course you've seen the top before, that's the El Centro north-south that we read in earlier. So that's a repeat. And the response is new, and you can see from the response that the system is trying the best it can to oscillate at 1.8 hertz. That's the dominant frequency of the response. And there is some resonant-like dynamic amplification because this peak here for the input's about 0.35 G's peak, whereas this is about 0.92 G peak. So yes, sometimes we can get dynamic amplification. We also get a relative displacement response, which is going to be at 1.8 hertz and Q is equal to 10, and that's relative displacement in inches, and having a peak absolute of about 2.8 inches. Which reminds me of something. Let me backtrack a few slides. So if you want relative displacement, you have to go click on plot types and ask for it, and then do your calculation. Okay, I mentioned pseudo-velocity before. Now it's time to discuss what is a pseudo-velocity. Well, it's kind of an approximate method here. It's approximate value of sorts, but we're going to say that it's equal to the angular natural frequency times the z, which is the z relative displacement. So again, omega sub n is the angular natural frequency, and PV squared, pseudo-velocity squared, is proportional to the peak energy input per unit mass, making it ideal for energy-based seismic design methods. And I've got a note here, Dr. Howard Gaberson and others have written papers showing that the dynamic stress is proportional to pseudo-velocity. And that was copied and pasted inadvertently to the top of this slide. So moving on, pseudo-velocity is the key link between ground motion and structural dynamic for a given earthquake response spectrum. Now we're about to do a response spectrum analysis, we're building up to it. Pseudo-velocity PV directly indicates the strain energy stored per unit mass in a single degree of freedom oscillator, making it more physically meaningful than the spectral acceleration or displacement alone. The peak ground velocity, PGV, approximates PV in the velocity-sensitive region of the spectrum, the lightly damped structures with natural periods between 0.2 seconds and about 2 seconds, covering most building and bridge structures. The PV, the pseudo-velocity, is approximately equal to peak ground velocity. That relationship provides a rapid damage estimate directly from the recorded ground motion without requiring a full response spectrum analysis. Let's then go to toolboxes and amplitude and unit conversion. Go to the SRS, and we're going to go tab and acceleration, velocity, and displacement English units. Let's go to the relative displacement metric for input. And our relative displacement, as you recall, was 2.8 inches, a little bit of rounding, at a natural frequency of 1.8 hertz. So the corresponding pseudo-velocity is about 32 inches per second, and then the corresponding acceleration is about 0.93 g's. Now these are estimates of pseudo-velocity acceleration, then using the relative displacement as an input. And those are pretty close to the values that we saw earlier, but we were not in the text area. F analysis at 1.8 hertz. We're not expecting those to be exact, but if we can get within about 1%, we're pretty good because there's a little bit of approximation going on here anyways. So next up, let's go back to the main GUI, and off to the side, we see a button called Calculate SRS. Let's click on that. And this is a shock response spectrum. Well, that's what we call it in aerospace. In earthquake engineering, it's simply called a response spectrum. The small wood ramp invariant digital recursive filtering relationship. So calculate, and we'll go to Centro north-south. And English units, process the entire signal. Time unit is seconds. Q is equal to 10, 1/12 octave. Now, for earthquakes, let's plot the frequencies, the natural frequencies, 0.1 to 10 hertz. If this was pyrotechnic shock, it would be 10 hertz to 10,000 hertz, typically. Include residual allows for one cycle of free vibration after the pulse is over with, and as long as we're letting that pulse have a time to decay to near zero, doesn't really matter. Including the residual then will result in a shock response spectrum that is greater than or equal to than if we did not include it. Usually we just go ahead and include it anyways, just be on the safe side. So here is the resulting shock response spectrum from the El Centro earthquake north-south, Q is equal to 10. We've got the peak acceleration in G's versus natural frequency in hertz. Now we see a positive and negative. Now the negative is the magnitude of the negative, because there's no minus signs when it comes to this type of log-log plot. Well, actually there's the exponents are minus signs, but what we do is we take the negative acceleration. We cannot take a log of a negative value, so we just take the absolute value of the negative and then tilt these base 10 log. So at a frequency of 1.8 hertz, then that blue positive peak should be about 0.92 G's, and that looks about right. So what we did is we did the time domain calculation for that one particular point. Now what the MATLAB did for the response spectrum is it did the same type of time calculation, but for a whole family of just dozens and dozens of natural frequencies. And MATLAB can do that a whole lot faster than we can. So we could have gone to the original program, the previous one that is, in the time domain, and in each 1/12 octave step, done the time domain small wood calculation, and then did the data reduction to the peak values. And we could have generated those curves ourselves, but we just let MATLAB do the whole family of natural frequencies, because MATLAB does it a lot faster, especially when it comes to bookkeeping and so forth. Now, this could be useful for a design situation. So let's say you have to, you're designing a structure to withstand an Centro north-south class earthquake, and you're trying to figure out what your mounted natural frequency should be. So your inclination might be to have a lower natural frequency to reduce the peak acceleration response. Well, that sounds like a good idea, and it may well be a good idea, but there's more to the story. So there's going to be a whole series of trade-offs we're going to have to take a look at. So we've got another type of shock response spectrum. It's the pseudo-velocity SRS, Q is equal to 10, and peak velocity in inches per second versus natural frequency in hertz. This is actually calculated from the relative displacement SRS, which is the next slide after this one. So we go to relative displacement SRS, and each relative displacement multiplied by omega sub n, and that's how we got this pseudo-velocity SRS. Well, we want to minimize pseudo-velocity because pseudo-velocity correlates with stress. What this is telling us is that we either ought to have a very low natural frequency or maybe a very high one, like a stiff mount, but it's kind of a stay-out zone here in the middle, because otherwise we're going to have some potentially high pseudo-velocities and some high stresses. Well, the third in the series is the relative displacement SRS, since Q is equal to 10, so peak relative displacement in inches, natural frequency in hertz. Now what this is telling us is that if we choose to have a lower natural frequency to minimize the response acceleration, the consequence or trade-off is we're going to have a high relative displacement. In fact, this value here may get to about 12 or so, maybe even higher than that, I think maybe 14 or something like that, inches now. We want a structure that's going to have to withstand that relative displacement? Probably not. So there are some very real-world trade-offs that come into play, and I'm not telling you what natural frequency to choose for your design goal, because I'm not that smart. But I want you to be aware of all the trade-offs involved and all the considerations, and depending on the sensitivity of your structure, the type of structure, the type of ground and the foundation, and quite a few variables at work, but damping plays a role too, is that you may prioritize one of these three metrics over the other in terms of relative displacement, pseudo-velocity, and acceleration. Now we've got a plot that's 3-in-1. We're continuing on with El Centro north-south. And this is nominally a pseudo-velocity shock response spectrum in Q is equal to 10. And we've got velocity in inches per second versus natural frequency in hertz. And this is called a tripartite plot, or sometimes Howard Gaverson called it a four-coordinate plot. And we have the red, kind of this dashed dot red line, for X, that's actually negative pseudo-velocity, the blue is a positive pseudo-velocity. And then the downward sloping lines are constant acceleration. The upward sloping lines are constant relative displacement. Now remember our favorite point, 1.8 hertz. So that pseudo-velocity comes out to be about 31 inches per second. It meets our expectations. Then the downward sloping lines reveal that acceleration peak is about 0.92 Gs, which also is in line with what we did before. And the upward sloping lines show that relative displacement at 1.8 hertz is about 2.8 inches. Now, we don't use this format much in aerospace, although we certainly could and probably should. It's more common to see tripartite plots or four-coordinate plots than for earthquake engineering. Although even in earthquake engineering, they might be used a little sparingly. But this format is certainly available to you in the GUI package. Oh, one other thing, I need to address this, is in earthquake engineering, that x-axis could be either natural frequency or period. Natural frequency is simply the inverse of period and vice versa. In aerospace, it's always going to be natural frequency. So if you want to convert that to the x-axis to period, time in seconds, you'd have to just imagine a vertical line going through 10 to the 0 and doing a rotation about that vertical line. So we'll do some response vector for earthquake engineering later on, and we'll probably go back and forth using natural frequency versus the period in seconds. Okay, we're going to do a little exercise here where we're going to be conservative, and we're going to take El Centro north-south and do a Q is equal to 50, which is 1% damping. That's very conservative, and that has the effect of increasing both the positive and negative by some amount. And then what we're going to do is take the highest point of them all, which is 1.5 Gs. Then we're going to add an uncertainty margin of 3 dB, and that's going to equal approximately to what we're going to call an equivalent static load of 2 Gs. So we're going to refer to the California Department of Transportation, Caltrans, and at one time they had a standard for bridges that the bridges had to withstand an equivalent static earthquake force of 2 Gs. And I think that number was derived, at least in part, from the consideration of the El Centro, just as we've done here. So the idea is to make life simple for the civil engineers that don't have a dynamics background. So just say to the civil engineers, make sure your structure can withstand a body load that's got an equivalent 2 Gs, and if it can do that, then it's good to go for an El Centro class earthquake with some margin to spare. I've got a few reservations about that. It can be overly conservative in some cases, but so be it. So here's the Golden Gate Bridge, and as I mentioned, now I say current. I'm not really sure if that is the current. It was at one time, but there may have been some revision in more recent years. But at least at one time, as I mentioned, when bridges were in California were required to withstand an equivalent static earthquake, EQ of 2 Gs. And again, I'm pretty sure it's based in part on the El Centro SRS with some dB margin. Now, it's interesting to think about the damping. I was very conservative with 1% damping. For a large civil engineering structure, and if it's just kind of a light wind and ambient type of a day, then 1% damping probably pretty realistic. But in an earthquake where there could be joint slipping and cracks in concrete forming, then the damping goes favorably upwards in the case of a major earthquake. So for us to take El Centro and just say 1%, that of itself is a layer of conservatism. Okay, one more slide today for our package. This is a launch vehicle at Vandenberg, and that's Central Coast of California. And the San Andreas Fault is about 35 miles inland. So that's a tall cantilever beam, and the launch vehicle may be on the pad for, say 5 to 10 days prior to launch. There's all sorts of checkouts that need to be performed. If it's a liquid engine vehicle, then the liquid oxygen and the liquid fuel need to be loaded up, and more checks, and then wait till the weather's good, and all the range tracking assets have to be up and running, and a bunch of other things. Now, the odds that a major earthquake in Central California is going to happen during any 5 to 10 day window is minuscule. But yet, the price tag of that launch vehicle payload, if it's a spy satellite, may be $1 billion or more. So there's a NASA handbook 705 that actually has a shock response spectrum for launch vehicles at Vandenberg. Now, we're not going to take a launch vehicle and mount it on a shaker table. It's too big and all sorts of other reasons. But we can do a finite element analysis. Actually, we can start with a single degree of freedom analysis, and then, as needed, work up to the multi-degree of freedom and finite element analysis. But this is the shock response spectrum from NASA Handbook 705, and acceleration g versus natural frequency in hertz. And then there's actually a family of 3 damping curves, which is nice. Now, the dashed line is the peak acceleration. It's actually the peak ground acceleration. And once we get above 1 hertz or so, there's this potential for dynamic amplification, as shown by those 3 curves there. So that's what mechanical structures do in certain cases, is they amplify energy, so response can be greater by several times the peak input acceleration. Now, eventually, at higher frequencies, all those curves would converge to peak ground acceleration. Let's think back to El Centro. El Centro was about 0.35 g peak ground acceleration. Here at Vandenberg, it's 0.26. Now, I'm going to kind of make a thought here, that an interpretation that I think that whoever created these curves was thinking that an El Centro class earthquake may happen at this point on the San Andreas Fault, which is about 35 to 40 miles away from Vandenberg. And then that person said, yeah, but there's then the distance attenuation. So the distance attenuation over 35 to 40 miles could conceivably bring the peak ground acceleration down from, say, 0.35 g's to 0.26 g's. Well, that's my plausible rationale for what you're seeing here. Don't know for sure, but sure makes a good story. Well, thanks for coming today. I look forward to seeing you again soon, and bye for now.